All right, good morning, everyone. This is for the next set of E and F days, March 18th to the 19th. We're going to go over the second day of 5.4 notes, and we'll go through the review for the 5.3 and 5.4 quiz. Okay, so a warm-up here, we have two indefinite integrals. Pause the video if you want to try these on your own, or I'll work here. Correction, they're definite integrals, not indefinite. So they are linear chain rules, so the E stays the same, the inside stays the same. We divide by 2, from -1 until 1. We plug in the 1 first, so that will give us e to the 2 minus 2, or e to the 0 power, over 2, minus, now we plug in the -1, so we're going to have e to the -4 over 2. I'm okay with this as your final answer, or you can see that e to the 0 is equal to 1. So we have a 1/2 minus e to the -4 divided by 2 is fine. Second one, be careful there. You have a 1 over x, and the integral of 1 over x goes to ln x. So the first term is x squared divided by 2. The second term is ln x from 2 until 6. So we have 6 squared over 2 plus ln 6. Put that in parentheses, minus parentheses 2 squared over 2 plus ln 2. 6 squared, 36. Divided by 2 is 18. So we're going to have an 18 minus 2 squared is 4. 4 over 2 is 2. So our constant term will be 16 plus ln 6 minus ln 2. This answer is totally fine. If you remember properties of logs separated with subtraction, we can condense those with division. So this is equivalent to ln of 6 divided by 2, or ln of 3. Both answers are fine. Okay, so two parts of the fundamental theorem of calculus. The first one says, if you integrate from a to b of little f of x dx, your answer is going to be big F of b, representing the original function, minus big F of a. The second thing is that if you derive an integral from a until x of f of t dt, deriving and integrating are essentially opposite operations. So all that's happening here is instead of having a t in the function, we have an x. And notice it's still little f. We still have our derivative function, the original function that was inside of the integral. The extension on this is, what if there's something other than just x? What if we create a chain rule during this process? So the textbook doesn't fully define this as a rule, because that upper limit could be anything. It could be x squared, it could be 2x, it could be square root of x. The key is that it's something besides x creating this chain rule. So I'm going to write it as if it were an x squared term up there. And then I would end up having f of x squared. And the additional piece that I need is we multiply by the derivative of that upper limit. So in this case, I multiply by 2x. And that would be my answer there. Okay, so to close out 5.4, I really just have a couple of additional practice problems that we did not necessarily see before in the other lesson. They're just a little bit more complicated. Okay, so the first one, t to the 5th, becomes t to the 5th minus 9t cubed. We want to notice that we are deriving an integral, so we're essentially doing nothing. The x goes in for the t spots, so we have x to the 5th minus 9x cubed. And that's it. Here, the notation changed a little bit. The t's and the x's are in different places. That's okay. They're telling us to derive with respect to t, so therefore the t gets to go in and replace the x. So we have secant of 5 t minus 9. Okay, so now our upper limit has something other than x up there. So we will replace the t's and we will multiply by 2x. Last one. We have cosine s to the 4th power. Derivative of cosine s is negative sine s. Okay. In all of these cases, my lower limit, my numerical limit, did not matter because during the derivative process, all of those constant terms would derive to 0. So regardless whether you have a 0 or a negative 6 or any other number, the derivative part of this process would cancel that constant out. Now, you did see in your homework, the extension problems, if I changed, let me go back to one that's a little bit easier. If I change number 21 and had an x on the bottom and an x squared on the top, and we're still doing dx of that. Okay. So in this case, you're still thinking, well, the integral gives me capital F of b minus capital F of a. The derivative takes the capital F and brings it back to the little f, so we're going back and forth between derivative and original function. We're ultimately ending up with the derivative. In the process, if you have a chain rule, you multiply by the prime of the inside, and if you don't, you just have to plug in. So here, my a and my b, neither of them are constants. Therefore, in the derivative process, nothing totally cancels out. So here we would have the complete f of b minus f of a. So we would have x squared to the 5th minus 9x squared cubed. Now that's a chain rule. I put in x squared, not just x, so I multiply by 2x. This is technically my f of b multiplied by b prime. Then I subtract my f of a, multiplied by a prime if necessary. In this case, a prime is not necessary because it's just 1. So we have parentheses x to the 5th minus 9x cubed.
What does Miss Bible say?
That's it for today, honey. Go ahead and you can do what you want. You can read another book on your iPad.
But what are the scissors for?
Do you want to do a cutting project?
Yeah.
Can you give me a couple minutes? I'm making a video for my students.
But for
All right,
you,
so now that you interrupted me, say hi to my students.
Hi.
Okay. All right. Sorry, guys. Okay, so I posted the 5.3 and 5.4 review for you. I'm going to go through here and work through some of the examples, but not all of them. I will make sure I put a full answer key up as an attachment under the outlined notes. Okay. So in this section, section 1, evaluate each definite integral. These are just reverse power rules and then plugging in your f of b over minus f of a. So this is FTC part 1. So for example, the first one, I would add 1 to that exponent, bringing it to x to the negative 1/5, and I would divide by negative 1/5 from 1 to 32. Plug in 32 first. Before I do that, I'm going to clean this up. Dividing by negative 1/5 is the same as multiplying by negative 5. So then I'm doing negative 5 times 32 to the negative 1/5 minus negative 5 multiplied by 1 to the negative 1/5. So 32 to the negative 1/5, feel free to put that in your calculator, but the fifth root of 32 would be 2. The negative is what flips it to make it a 1/2. So we have negative 5 multiplied by 1/2, and then we have plus a 5. So negative 5/2, or negative 2.5 plus 5 will give us a positive 5/2. Okay. Let's take a look at the secant squared one, for example. So secant squared, if that's on the quiz, well, now it's open notes on everything anyway, but secant squared would be given naturally. It returns back to tangent x from 0 to pi over 3. We put in pi over 3 first, put in 0 second, go to your unit circle. So pi over 3 is your 60-degree angle. So the cosine is a half, and the sine is root 3 over 2. So we have root 3 over 2 divided by a half, minus tan at 0 is 0 over 1. So this ends up becoming root 3. Okay. And let me do number 6 for you. So number 6 starts as a quotient rule. Remember, you have to avoid those. So I have to write this in a simplified way to begin. I need to divide the x squared into each term. So x squared divided by x squared is 1. Thinking of root x is x to the 1/2. X to the 1/2 divided by x squared, or subtract your exponents. So that's x to the negative 3 over 2. Okay, so now I have two terms that I can antiderive. One returns back to an x, and x to the negative 3/2. If I add 1 to it, I have x to the negative 1/2 divided by negative 1/2 from 1 to root 2. So then I plug in root 2 first. Put this in your calculator. All right, guys, honestly, I don't have my calculator handy. I will put a decimal answer for this up later on, but for now I'm just going to move on. Okay, the second part is FTC Part 2. This is where we're deriving an integral, so we're doing opposite operations here. The key is look to see what the upper limit is. The lower limit, as long as it's a number, does not matter. So having a 0, we don't need to use it. We need to acknowledge that we're deriving an integral. We're not changing the expression that is inside of that integral, except for we are replacing the t with the x. Okay, so number 1, it's just an x up there. We do nothing besides swap them out. The second one, it's a root x up there. So we start the problem the same way, replace the t with the root x, and we multiply by the derivative of the root x. Same thing down here with sine of t squared. Root x is what we're plugging in. So sine of root x squared is just sine of x. And we multiply by the derivative of root x. Okay, so that's the review for your quiz. The quiz will happen on Friday. It is created already, but it will not become available until Friday morning, and it will close Friday night. So you have any time during the day on Friday to take the quiz. I've given you 60 minutes, which is more than enough time for both students who need extra time or not. So please do your best to submit your quiz through the assessment. I know that there was some trouble uploading, so if you have to email me, but try your best to submit through the assessment online. All right, thanks, guys.